Good morning. My topic of pre-submission seminar is System Design and Integration of a Smart Cell Architecture for Computationally Intensive Application, under the supervision of Dr. Vaishali sir and Dr. Tehare sir. This is my registration. This is my outline. Now, introduction. Now, computationally intensive application generally it applies in the applications like wireless communication, multimedia. When we are implementing this type of system, so whatever so it goes with the maximum arithmetic operation. So we can categorize this as under computationally intensive application. So by designing this type of system, so the high performance, we have to maintain performance high, low power consumption and flexibility. These are the design challenges. To implement this computationally intensive system, these are the platforms available: general purpose processors, then ASIC, and reconfigurable architecture. If we compare the performances of these with respect to flexibility and performance of power consumption, so we can see that ASIC is this is more power efficient and performance is good, but it is not flexible. So we cannot modify any changes in the architecture or hardware. General purpose processors are very flexible, but it is less power efficient. So the another alternative is to use a reconfigurable system, which is still dominated by a field programmable gate array. So again, reconfigurable system is generally categorized into two categories: field programmable gate array and post-gate reconfigurable architecture. So this is a better option to, if we want to make a system flexible and power efficient. So this is a better solution to use reconfigurable system, which is again categorized into two: field FPGAs and post-gate reconfigurable architecture. So if you compare FPGA with post-gate reconfigurable architecture, so what is the difference in these two architecture? So FPGA is in FPGA there is a bit-wide computation. When we are going to implement any circuit or hardware in FPGA, so it configured bitwise, and it is so FPGA is suitable for low power, small applications. When we are implementing a large application on a FPGA, so it consumes more power and more area. So we can say that FPGA is not suitable for computationally intense applications. So another alternative is to use post-gate reconfigurable architecture system. So post-gate in reconfigurable architecture system, so bit configuration is worldwide. Instead of single bit, we are configuring 8-bit multi-bit, 8-bit, 16-bit and all this. Now this is a basic architecture of a post-gate reconfigurable architecture. In post-gate reconfigurable architecture, we have arrays of arithmetic and logic units, and which is generally interface with configuration memory and controller. So my motivation. So modern motivation of research is to modern portable device like mobile phones and laptops and medical instruments. These are more battery portable. So this is a battery oriented. So power consumption is a limitation for this. So we want to reduce power consumption for this type of application. At the same time, to cope up with the rapidly changing technology, this hardware should be reconfigurable. So these are the two. So up till now, the FPGAs are the reconfigurable, most popularly reconfigurable system in which we are implementing this type of application. Another alternative is to design a post-gate system for this applications, like for portable devices, so that power consumption can be reduced, and again we can maintain the reconfigurability of the system. Now, so our objective of the research was to design this type of system. So first I have designed a array of a post-gate architecture. Then I have integrated this with the memory and controller. After that, I have optimized the system for less power consumption, and then I have implemented some benchmark application on this architecture on FPGA to compare the results. So these are the literature survey So these are the different architectures that is developed from since 1996 to 2015. So these are the categorized. So what are the, this is the PE arrangement, how the PEs are arranged. So reconfigurable model, is it statically reconfigurable or dynamically reconfigurable, data width and application domain. So this is my work. So I have designed a 2D dimensional array which is statically reconfigurable 16-bit, and this is use parallel processing and can be so DSP like applications can be implemented on the system. So these are the work carried out. I have designed the CGRA system, then I have interfaced this CGRA system with memory and controller. Then I have mapped FFT algorithm on this architecture, then FR algorithm on the same architecture. Then I have done power analysis of a Postgain architecture for both algorithms. Then I have implemented a FFT and FR on FPGA, and then I have compared the results.
Why the FFT and FR is chosen?
So because FFT and FR are the most popular algorithm which is generally used
or
in
most critical algorithm as far as the competition.
Yeah, this is also critical as well as most popularly used algorithm. As the now like 64 point, as the point of FFT increases, the computational also increases, complexity also increases. That's why. So I have implemented from 2 tab to 64 tab FFT in the same architecture, so that we can show the difference between the power consumption. Now this is the architecture that I have designed. This is the overview of a architecture that I have designed. I have designed the 16 by 4 by 4 array of a CG array. Then I have connected with the instruction memory and controller. So this is a design of a single processing element in which the ALU will perform basic operations, arithmetic and logical operations, and the data will come from on-chip connections, means from other memories, from other PEs and memory, data memory, and then again it is circulated to other PEs and memory. Now this is the RTL view of a single PE that I have implemented, and this is the array of a 16 PE. You can show this is a 16 PE which is connected with each other. Now this is an interconnection of a processing element that I have done. So in other CG array they are using the another switching matrix to connect the PEs to another PE. So instead of that I have implemented this type of architecture in which the same PE will communicate. So instead of separate router, because if I implement a separate router for communication between the PE, so it increases the area as well as power consumption. So instead of that, I have implemented the router structure in the same PE.
What is core? PE is working as a router.
So PE will also transmit the data. So it is working as a router. So same time means it will process and it can transfer the data.
4 inputs, 5 outputs.
So yeah. This is a logical diagram of a router architecture in which I can see that this is a route. This is an instruction that I will use. Depending upon this instruction, it will pass the data from east P to north, west, south P. Then this is 4 is the data from the same P in which this is implemented.
What do you require?
Because so this is the data from other PEs, and this is the same PE.
Okay.
Now this is a simulation for a PE interconnect. In this you can see that this is a route instruction. According to this route instruction, the data will be, this is from east, west, north, south PE. This is the input, and these are the east, west, north, south output. So you can see that the data from input is transmitted to north P. From east P, the data is transmitted to north P. Now this is again same time. So I have implemented this P enable pin here. So whenever this pin will have, the P processing element will perform the operation. Now in this case, I have given the instruction to like this. This is a 000 is an instruction for addition. Now here the data from mux immediate this memory data, and this ALU1, this will get added. So this instruction I have given. So after this P enable is high, then and then only it will perform the addition. Otherwise it will not perform operation. So again this is useful for reduction in power, because whenever operation is required, then and then only we will perform the operation. So we can reduce in this way the dynamic power. Now this is the instruction set or controller format for programming this architecture. So here you can see this is an 8-bit data path which is used to give data, means data path for performing operation of a PE. So which two data will get perform operation. So this is opcode, which is the operation, logical or arithmetic operation is specified through this opcode. Now this is a PE address which is used to give address which PE will perform this operation, and then this is a PE count. Now so to enhance parallel processing, I have given a PE count, means how many PE will perform these operations. That is also, so it enhance the parallel processing of the architecture. This is PC control through which we will give the program controller the controlling instruction. Now this is a router address that I have just discussed how the data will communicate from PE to another PE. And this is a constant. If you want to give some constant, so you can give the immediate data through the instruction also, and these are the results. Now this is a complete CGRA system that I have developed. Now this is a CGRA unit which includes 4x4 processing element that I have the interface with controller, instruction memory, and program counter. Now this is a simulation of a complete system. In this case you can see that these are the output. Now depending upon the instructions here, so the different P's are performing different operations. Now you can see that the 4 P's, so I have given an instruction that 4 P will perform some operations parallelly. So you can see that the 4 P's are performing operations in parallel. After that the next P will perform operation. After that next P, and in this way I am getting the results according to the instruction that I have written in the instruction memory. After that I have done the mapping of FFT on this architecture. Now so FFT generally it's a discrete Fourier transform for a data vector. FFT is a DFT algorithm which reduces number of computation needed for an input. So now for 2-point DFT, we have a 2-point butterfly unit. Now 2 input, which will have 2 inputs and 2 outputs. So where twiddle factor is given by this formula, and where here n is equals to 2 and k is equals to 0. So the twiddle factor for this is 1. So if we simplify it, so you can express through this butterfly diagram this equation, like x of 0 is a of 0 plus twiddle factor into b of 0. And so from this you can see that it requires for a single butterfly unit, to implement single butterfly unit, we require single multiplication plus 1 addition and 1 subtraction. So we have to write down for implementing this butterfly unit on this architecture, we require 1 multiplication, then 1 addition and 1 subtraction. So if in case of a complex input, we can write down this instruction in this way. So here this A is a real and imaginary output can be calculated. So if I am implementing, in this diagram I have implemented a 2-point FFT. So for implementing 2-point FFT, this is a complex data I have taken. So twiddle factor will get multiplied, means real and imaginary part will get multiplied. So I required a 4 multiplication, and after that the 2 additions and 2 subtractions that are needed to implement complex 2-point FFT. After implementing, I am getting the result. So this is the result after implementing 2-point FFT. The same way, if I want to implement 8-point FFT, so you can see here we require a 12 butterfly diagram, means for in 8-point FFT, so 12 butterfly units are required. So 4 butterfly unit required in the first stage, second stage and third stage. So to implement, so this is a data flow diagram for 8-point FFT. Here the 4 inputs like this is x4, x6, x5 and x7, that is multiplied with the Twiddle factor. So this is get multiplied with the Twiddle factor, and then this is added with the another input, that is x0, x2, x1, x3, and after that the same PE will perform subtraction. So and this 4 multiplication will it is done parallelly. So 4 multiplication will take place in parallel. After that 4 addition will take place in parallel, and 4 subtraction will take place in parallel. So in this way, to implement a single butterfly unit, 4 butterfly unit, we require 3 clock cycles. So this is a simulation result for implementing 8-point FFT. So in this way, I have implemented 2-point FFT, 8-point FFT, 16-point, 32-point and 64-point FFT on the CGI architecture that I have designed. Now in this, you can see that and I have calculated the power, static power and dynamic power. So these are the chart. So in this chart you can see that as the area is constant, so static power is almost constant. We are not getting deviation in the static power. Only dynamic power is increasing because the number of arithmetic calculations are increasing. So dynamic power is increasing. So these are the total power that I have calculated, and this is the number of clock cycle which is required to complete this calculation. Like for 2-point FFT it required 4 clock cycle, 8-point it required 12 clock cycles, and this is the execution time that is needed to calculate 6 different FFT algorithm. Now this is the power consumption. Now again the same I have same algorithm FFT 2-point, 8-point, 16-point, 13-point I have implemented on the FPGA also. So again I have compared the power. So this is the static power and dynamic power for the FPGA. So here you can see the difference. If I am implementing this on FPGA, so you can see that the static power is also increasing as the higher versions of FFT were implemented on FPGA. Because to implement this type of FPGA, the area is also increases. That's why dynamic power and static power is also increasing. In our device, the static power will remain constant because the area will remain constant for this. Now, this is the comparative chart. So you can see that for 2-point FFT, the power consumption in FFT and our design architecture is almost same. But as the complexity increases, the power consumption in FPGA is become it's very high, but in our system it is less, or it remains constant. So there is a very less changes in the power consumption as the complexity of the algorithm increases. Same way I have implemented a 4-tap filter on the system. So for implementing 4-tap filter, you can see that the single input is multiplied with the some constant. So 4 multiplication is required and 3 addition is required. So that thing I have implemented in this 4 multiplication, which is multiplied with the input and some constants are there, 4 constant, and then it will get added sequentially. So I am getting the output. So this is a simulation result for 4-tap FR filter. Again I have compared I have implemented a 4-tap, 8-tap and 16-tap FR on the CGI system, and again I have calculated the power. So again the power consumption, static power will remain constant as the area is same and dynamic power is changing. And again I have compared the same data with the FPGA. So same tap filters are implemented on the FPGA, and so again as the complexity increases, the static power of FPGA will increase, dynamic power will also increase. So power consumption in FPGA is very large as compared to the CGI. So this is a comparative chart that shows that as the complexity of the system increases, the power consumption increases. So these are the some results from power analysis. The power report shows that the overall static power of a novel Gaussian architecture is 160 milliwatt at 100 megahertz frequency and almost constant as the area of the architecture is fixed. Dynamic power is gradually increases as the length of algorithm increases. 64 point FFT, it is 47% of a total power as compared to FPGA. To the system, the architecture consumes less power. So again, in this, in architecture, as we can see, if we are going to, if we are implementing 64 FMT, or if I want to implement higher type FFT, so number of instructions will increase. So the size of instruction memory is also one of the important parameters in the CGRA design. The increase in size memory can result in increase in static power and area of the architecture. To optimize this system, this research also proposes a novel method of memory looping. So here I have used, so instead of writing all required instructions, some common instructions are repeated by doing looping through a program counter. So again here, this control word will give instructions. In this I will read some I will write some control word key, so that control word is for how many looping you require and how many instruction will be looped. So that instruction I have given. So you can see here for 0, this is a address of the instruction memory. So you can see that 0, 1, 2. So this is a instruction. So 2 times this 0, 1, 2 instructions are repeated. So instead of writing same instruction again and again, we can loop that instruction using instruction memory management, so that you can reduce the memory area. So memory requirement will be reduced and you can write efficient more and more complex instruction in a minimum instruction memory. So this is the RTL view of a modified program counter. So here we have seen, I have also given the comparative memory saving. So for 8-point FFT, so if we are not doing memory management, then we require a 6, 12, 48 and 96 instruction memory. So after implementing this instruction memory management, I am getting 50%, so I am getting these results. This I have again done the comparison with the other CGRA that already developed. So these are the other CGRA. From that you can see that the proposed architecture again consumes less power.
This is for the 8.6.
No, this is for 64 FFT length. So actually I have compared only 64-point FFT. I have compared the power result. So this is a CREAMA architecture, Avatar architecture. So this is a name given to the different architecture. Smart Cell is another architecture. So in that architecture they also implemented a 64 type FFT and they have also calculated the power. So the power consumption is given in this chart. So this is my proposed CGRA. I have also implemented a 64 FFT. I am getting this much power.
All the other 3 are the latest work or?
So this is actually this is not the latest work. This is a Smart Cell architecture. I have taken this architecture as to design my architecture. So this is my reference architecture. So I have considered this architecture.
When was it? Is it recent or past?
It is this is a paper of 2009 actually, Smart Cell architecture.
After that, no work in Smart Cell?
No sir. After that I have compared this with another architecture, CREAMA and Avatar. So again the comparison.
They are after 2009.
This is from 2012. This is my conclusion. As the number of calculation increases, static and dynamic power consumption. This is my publications. These are the references.
Okay. So, your title says Smart Cell Architecture,
yes,
Integration.
Yes, sir. Sir, actually, I have an integration of a Smart Cell architecture. for computational intensive
No,
application.
integration of smart cell.
So smart cell architecture actually, this is a CGRA architecture. Smart cell architecture is a CGRA. So I have designed that CGRA architecture. I have integrated this with the instruction, memory, and controller.
Hello.
That's why I have given this type of title. Integration of the smart cell architecture.
Computationally intensive application.
So computationally intensive application means
What you have done is architecture, you have compared, you found that yours is better than that. But now the next part of the title says for computational intensive application.
that I
Can
have
you take an
Yes,
example and then
sir,
You
I
have
have
not taken
taken.
any example
any
of
example?
application.
In the presentation I didn't see.
Sir, computationally intensive application means which requires lot of lot of
Generic
arithmetic.
statement, but now you have
No, so I
researched.
have taken an example of a FFT and FI filter. So as the, you can say the intensity, like instead of implementing, so in this case you
No,
can.
can you take an example of intensive computation?
So computational intensive application like higher point type.
You say
FI
FFT
filter.
is computation intensive.
Yeah, because if I compare 2-point FFT with 64-point FFT, so 64-point FFT is more computationally
No,
intensive.
I am just trying to find out from your title.
Yes.
System design and integration of smart cell architecture for computationally intensive application. Justified.
So, just to take.
Of course, you have to
Yes.
say that.
No, sir. Actually, this is a computational intensive application means a lot of.
Numerically, can we not some take application and then show CGA versus FPGA
Actually, you are
versus.
saying that you have taken 64-point FFT and that is computationally intensive.
The
I think you are
person,
saying like that.
No, sir. Actually, if we compare 2-point FFT with 64-point FFT, so I have shown the result. I have implemented 2-point FFT on FPGA and 64-point FFT on also on FPGA. So you can say that as the complexity of the algorithm increases, the power consumption increases. The same algorithm I have implemented on my CGI
there are some
architecture.
algorithms which are more complex than FFT. For example, adaptive filter.
Yes.
Now, where to stop? Where research has some what we can say scope.
Yes, sir.
Okay.
So my,
Computational intensive is the general term. You put the limit on that.
yeah.
Okay. Because other person may say that the adaptive filter is a more complex
Yeah, that is there, sir. But
Now, can you put some performance index or limit on the second clause, computational intensive?
If you are asked to change the title, what is it? Suggest it. What do you suggest?
I think
You don't want to. You don't want to change.
according to my opinion, what I thought.
At this
That's okay,
stage,
that's okay. Not,
at this stage, she could not change, I think.
Mhm.
Title change is not allowed. This is a pre-submission section.
then can you take some example other than
Let us
FFT?
take the liberty of, let us put some performance index there.
Index.
Up to that level complex,
Yeah.
intensive like that.
Actually, sir, I have designed an architecture. Okay, so in this architecture,
Other than FFT, can you take something? Can perform and say
I can take
This is-
my matrix multiplication also.
any,
Yeah, I can
any
take my.
computational intensive.
Yes.
Example you take.
Yes, you consider 2-3 classes
Yeah.
of computational intensive. One is FFT class.
FFT you have taken, fine. That's
Yeah.
fine. One more, you just take.
One more
Everything is ready, no? You just have
Yes,
to
sir.
take another example
Yes.
where it is computation,
yeah,
intensive
yeah.
computational thing.
or some random signals will also do. Probability and random signals example.
Wherever you think there's a
So actually, limitation from my side is that I have whatever I have instruction I have to make, that is manual. I don't have any compiler for this. So manual mapping is there. That's why the limitation is that until unless I don't have that software, so I cannot realize any application. So
No, I'm not realizing. Now you have CGPA,
yeah, CGI.
CGS, sorry. See. So there you took your FFT
Yeah,
and also FIR
yeah,
and show that from 2 point to 64 point.
yeah,
My design is better than this.
yes,
Can you take one more example
yes, sir.
other than this and then do and supplement
Yeah.
and write?
yes,
That's it.
yes.
You got all right, Dr. Pankaj?
Yeah. Right, sir. Actually, she has to show some. She has to take some example on the basis of which
Then,
she has to show the
say
result,
some.
her result and
Yes.
the previous result.
One more class.
One more algorithm.
It is easy. The same structure can be extended.
No, sir, I have to write some instructions also.
Yeah.
And
Yeah,
that is
doable,
fine.
sir.
Yes.
Okay, thank you.
Suggestions are very good.
Any questions, please? No?